Hello again. We'll continue with the DA converters as promised at the end of the previous video. First, we'll look at different types of DA converters. In the following, without claiming completeness, we will build up from the simplest types towards complex solutions.
Hello, that's right. Let's get started. For example, Gergő, there's a DA converter right in front of you.
Do you mean this toggle switch?
Yes, that's exactly what I mean. The simplest example, which you might not think of as a DAC at first, is a switch that can switch its output between ground and the reference voltage. This is actually a 1-bit DAC and is very simple to implement on an integrated circuit. But let's look at some more serious DACs. The first group is the integrating type DACs. These are implemented using pulse width modulation, PWM, or pulse density modulation, PDM, and analog filtering. The first of these is the PWM-based DAC. The ratio of the time between the two positions of the switch described before is determined by the input digital signal within a fixed time slice. An additional element is a low-pass filter that allows the output voltage or current to be averaged. In many cases, the low-pass filter is the device to be controlled, for example, a motor, or, in the case of an LED lamp, the human eye. The PWM output is available in most microcontrollers with hardware support, but can be implemented in a limited way in almost any microcontroller by software adjustment of a digital output.
Another integrating type of DAC is the sigma delta DAC, which is based on oversampling. Here, the principle of operation is very similar to the PWM-based DAC, only this solution uses PDM, that is, instead of variable width pulses, it sets the output to either 0 or 1 with a fixed frequency. The advantage of the sigma delta DAC is that it can achieve high resolution and very good linearity at low production cost. This is why audio DACs are usually based on this technology.
The next group is the binary-weighted DACs. DACs in this category have separate electronic components and switches to generate a signal proportional to each binary local value. These DACs have a high update rate, but the production of high-precision versions is not straightforward due to the difficulty of producing the required proportional steps in the integrated circuits. Depending on how the proportional signal is produced, a number of DACs fall into this family. For example, the first is the switched resistor DAC. The figure shows an example of a 3-bit DAC connection. The resistors associated with each local value can be connected to either ground or reference potential, depending on the digital input value, so that the resulting resistances obtained by the parallel switched components determine the output voltage.
There is also a switched capacitor DAC. The implementation is the same as a switched resistor DAC, except that here capacitors are used instead of resistors.
The next type of binary-weighted DACs is the R2R ladder DAC. You can see this in the figure. Compared to the switched resistor DAC, this implementation uses R and 2R value resistors, of which the 2R component is usually implemented on the integrated circuits with two resistors of size R in series, shown with red mark. This makes the DAC much easier to manufacture and less sensitive to the precision of the R resistor value. The switches allow us to switch the resistors to ground or reference potential. The voltage value to the operational amplifier is obtained by connecting the resistors in series and in parallel. For example, if only the switch called MSB is connected to the reference potential and the others to the ground potential, the equivalent resistance of the resistors outside the MSB switch is 2R, so the voltage across the positive leg of the operational amplifier is exactly half the reference voltage. It may be a bit hard to understand at first, but draw the circuit on a piece of paper, and if you rearrange the resistors, it may be a bit more transparent. That's what I did.
The next type is the cyclic serial DAC.
It's very important to note that it is not in the family of binary-weighted DACs, because in a cyclic DAC, the result is not obtained in one step, but one by one. The local values of the binary input are passed through, and the corresponding outputs are determined one by one. Let's take a look at the diagram. The process starts at the smallest local value, in this iteration n is equal to 1, which is used to connect either a reference voltage or a ground to the summing input of a 0.5 gain amplifier, so that the number of summing steps is equal to the number of local values. The figure shows a simplified DAC architecture and the conversion steps for a 4-bit input code with the output values for each clock cycle. Let's take a closer look at this. On the left, you can see the digital number we want to convert to an analog signal. This number is 1011 in binary, but since we start the conversion with LSB, the smallest local value, it will be 1101 in reverse order. The voltage V0, 1, 2, 3, 4 is always measured here at the symbol Vn. Initially, the system is in the default state, so in iteration 0, when n is equal to 0, the voltage is 0. So V0 is equal to 0. When n is equal to 1, the bit is 1, so the reference voltage, so to speak, arrives at the circuit's input and then passes through the 0.5 gain amplifier, so V1 is half the reference voltage. In iteration 2, the bit is again 1, so the reference voltage also arrives at the circuit's input. Note, however, that because of the feedback here, we get V1 back on the other branch, which was Vreference divided by 2. Thus, Vreference and Vreference divided by 2 from the previous iteration arrive at the input of the amplifier together. When the amplifier halves these, we will get V2, which is Vreference divided by 2 plus Vreference divided by 4. But in iteration 3, the incoming bit is 0, so there is nothing coming from the left input. However, from below, from the feedback branch from the previous iteration, comes V2, which is Vref over 2 plus Vref over 4. If the amplifier halves this, it becomes Vref over 4 plus Vref over 8. In iteration 4, a bit is added again from the left, to which the result of the previous iteration is added in the same way, and then the whole is halved in the same way as in the previous iterations. This gives us V4, which is equal to Vref divided by 16 plus Vref divided by 8 plus Vref divided by 2. This will be the result of the whole DA conversion because there are no more local values. If you add up these fractions, you get 11 Vref over 16, which is good because if you remember, our digital number in binary was 1011, which is exactly 11 in decimal.
Now, it's time to look at the DA conversion in practice. It's important to note that we'll be using a different hardware here than in the written curriculum on the website, but you can get this Nucleo card more easily, so you can try out the program we're going to write together at home. Let's take out the development board, which is a Nucleo F446ZE. What do we need to know about the digital to analog converter of the microcontroller on it?
In fact, this is a Nucleo F446ZE with an STM32F446ZE microcontroller. This microcontroller on the development board contains two independent R2R DACs with voltage outputs. Conversion can be done in 8 or 12-bit resolution, depending on the setting, with the two channels independent of each other or in synchronous mode. The outputs can be separately calibrated, and there is the option of switching a built-in triangle and noise signal to the DAC input. The DAC pins can also be used by other peripherals, so if you want to use the DAC function, you will need to configure it accordingly. The converter can be used in direct memory access, meaning DMA mode, which can reduce the load on the microcontroller's CPU. In this figure, we can see the simplified block diagram of the DAC from the microcontroller's datasheet. The rectangles represent the registers and logics, and the arrows represent the direction of the data flow. Numbers in square brackets, such as square bracket 3.0, indicate which bit of the register is being addressed. The X at the end of the names indicates that the bits for each channel are found separately in the microcontroller, but are only shown once in the figure for simplicity.
Let's look at each element of the block diagram separately.
The first is the DAC control register. Channels are controlled via this register. The lower 16 bits of the 32-bit register are assigned to channel 1, and the upper 16 bits are assigned to channel 2. It allows you to enable certain functions of the channel, the DMA, the trigger, and the built-in signal generator. The trigger selector transmits the trigger condition set in the control register to the control logic. The conversion can be triggered by the counter, external signal, or software. If these triggering options are not used, the outputs of the DAC will be updated after every clock cycle, but with any triggering option, this will only occur every 4 clock cycles. Let's look at the data hold register, or DHR for short. This register is used to write the digital input value of the DAC conversion. Depending on the setting, it accepts an 8 or 12-bit number, left or right aligned.
A little lower down, here you can see the data output register, or DOR for short. It is not writable directly, but handled by the control logic. This will be the input to the digital to analog converter.
This is the control logic in the middle. It controls the DAC based on the configuration written to the control register. It is also responsible for handling DMA requests and interrupts, and for transferring data from the DHR to the DOR. The control logic also generates the signal for the built-in signal generator.
And this is the digital to analog converter at the bottom. The outputs of the DAC can be updated independently or simultaneously. To further increase accuracy, it is also possible to use an external reference voltage via the VREF plus leg.
Based on the digital input of the DAC, the analog output can be calculated using the following formula. The V output is equal to the digital input value, that is the DHR register, multiplied by VREF over 2 to the nth power minus 1, where n is the number of bits. From this, we can calculate the required input value needed for 1 volt analog voltage at the output. With a resolution of 12 bits and the reference voltage of 3.3 volts, the formula is as follows. The digital input value, that is the DHR register, equals to V output multiplied by, in parentheses, 2 to the nth power minus 1 divided by VREF, which in this case is equal to 1 volt multiplied by 4095 divided by 3.3 volts, and this is equal to 1240.9. Since integers can be written to the register, the closest integer value to 1 volt output is 1241, so this is what must be loaded into the DHR.
Now, let's try the DA converter in practice.
But the bad news is that this will only happen in the upcoming video.
However, this will be the most interesting part of the chapter, so stay tuned.
That's right. See you all!
Bye!